Welcome to this lecture on branching and logical control in C programming. In this session, we'll explore how to use conditional statements like if else, and switch to make decisions in your programs. You'll learn how to detect equality, check ranges, combine logical expressions, avoid common mistakes, and work effectively with Boolean, character, and string data. By the end, you'll understand not only how to control the flow of your program, but also how to write cleaner, more reliable decision-making logic. Whether you're a beginner or just refreshing your skills, this will build a strong foundation for mastering conditional logic in C. Branching and logical control in C programming by the programming professor. Let's take a look at the outline for this lecture. We'll begin with an introduction to conditional branching in C and how to use if statements for simple decision-making. Then we'll move into more advanced branching, such as comparing values, detecting ranges, and using logical operators to handle more complex conditions. We'll also discuss gaps in logic and how to handle multiple conditions effectively. Toward the end, we'll look at switch statements, Boolean variables, and string comparisons. And finally, we'll cover important concepts like short-circuit evaluation and floating-point equality to avoid subtle bugs in your logic. To start with, let's talk about the basics of if statements. In C, a branch allows your program to make decisions. It only executes certain instructions if a specific condition is true. A common example is checking if a user is eligible for a discount. For instance, if the user's age is greater than 65, we can use an if statement to print a message that says they qualify for a senior discount. If the condition is false, the code inside the block is skipped entirely. This is how you introduce logic into your programs. It's a foundational skill that you'll use in nearly every program you write. Let's take a closer look at a real-world example using an if statement to compute the absolute value of a number. In this case, the program prompts the user to input a number. Then it checks if the number is less than 0. If it is, the number is converted to positive by assigning it as -x. If it's already positive or 0, the if condition is false and the block is skipped. The final step is to print the absolute value of the number. This kind of logic helps programs respond dynamically based on user input. You can also see a flowchart on the slide that shows the decision process from input to output, with a branch based on whether x less than 0 is true or false. Now let's build on that with if-else statements. These provide two possible paths, one for when the condition is true and another for when it's false. This makes your logic more complete because it guarantees that one of the two blocks will always execute. For example, consider a program that sets an insurance rate based on age. If the person is under 25, they're assigned a higher price. Otherwise, they get a lower price. The if-else structure makes this logic clear and ensures that a price is always assigned, no matter what age the user inputs. It's like flipping a coin. Either one branch or the other will run, never both. In this example, we look at how to use an if-else statement to determine the maximum of two values. This is one of the most common use cases for branching logic, deciding between two alternatives based on a comparison. The program checks whether x is greater than y. If it is, then maxval is assigned the value of x. Otherwise, it's assigned the value of y. This kind of branching is useful when comparing scores, prices, or any two values where you need to choose the larger or smaller. The key takeaway here is that if-else allows a program to selectively run one block of code or another based on a condition. When only two outcomes are possible, like here, it keeps your logic clean and easy to follow. Here, we extend the if-else concept into a full if. Else if. Else chain to assign letter grades based on a numeric score. The program checks if the score is greater than or equal to 90. If so, it assigns an A. If not, it checks if it's at least 80, then assigns a B, and so on. Finally, if none of the conditions are met, the program assigns an F. This kind of structure is used when you have more than 2 possible outcomes, and each one depends on a range of input values. Only one block will be executed, even if more than one condition is true. The program stops checking as soon as it finds a match. This approach is especially helpful in applications like grading systems, pricing tiers, or user access levels. This example focuses on using if statements to detect whether 2 values are equal. Equality checks are common in all types of programs, whether you're comparing user input, checking configuration settings, or validating results. In C, the equals operator is used to check equality. For example, if A equals B is true, then both variables hold the same value, and the code inside the if block will execute. This slide also includes an example checking to see if a couple has been married exactly 50 years. If so, a special message is printed. It's a great example of how a simple condition can be used to influence program behavior based on user input. Now we look more closely at the equality and inequality operators available in C. These include equals for equality and exclamation point equals for inequality. These operators are essential for making decisions in code, especially inside if-else-if and while statements. Each one compares 2 values and returns either true or false. The slide also reminds us to be careful not to confuse equals with equals. The single equals sign is used for assignment, not comparison, and using it by mistake can cause logic bugs that are hard to detect. Understanding how to use these operators correctly is foundational for building decision-making structures in your programs. In this example, we apply conditional logic to determine whether a number is even or odd. The key here is using the modulo operator, which returns the remainder after division. If a number modulo 2 equals 0, it's even. Otherwise, it's odd. The program reads an integer from the user and checks usernum modulo 2 equals 0. If true, it prints that the number is even. Otherwise, it prints that it's odd. This example is great because it combines mathematics with conditional logic and is widely applicable. For instance, in filtering data, alternating behavior, or checking input. The use of if-else here demonstrates how simple logic can yield useful real-world functionality. Multi-branch if-else statements let you handle more than 2 outcomes by checking conditions in sequence. This structure is especially useful when you're comparing one variable against several different constant values. For example, if you're mapping the number of years a couple have been married to an output message, you might check if the num years is 1, 25, or 50, and if so, display a specific output message. Each else-if handles a specific value. Once a condition is true, that block runs and the rest are skipped. This is a more scalable and organized approach than nesting multiple if statements or using many independent ifs, which can get confusing and inefficient. It's also an alternative to using a switch statement when your comparisons involve more complex logic than just constant values. Remember that the order of your conditions matters. Place the most specific or most likely ones first to make your program both efficient and readable. This slide explains how C compares characters, strings, and floating point numbers, and the important distinctions between them. When you compare characters, you're actually comparing their ASCII values. For instance, capital A is 65 and lowercase a is 97, so capital A is considered less than lowercase a. But with strings, the equals operator doesn't compare contents. It compares memory addresses, which leads to unexpected results. To compare strings by value, you must use the string compare function from the string.h library. If the strings are equal, it returns 0. Another important point is about floating point numbers. Avoid using equals equals to compare them. Due to how they're stored, two floats that should be equal might differ slightly. Instead, compare them using a tolerance or epsilon. Understanding how each data type is evaluated ensures your comparisons work as intended. Relational operators in C let you compare two values to see how they relate, whether one is greater than or less than the other. These operators include less than, greater than, less than or equal to, and greater than or equal to, and they're crucial in any conditional logic. For example, if x is 3, then x less than 4 is true, while x greater than 3 is false. Each expression evaluates to a Boolean value, either true or false, which you can use inside of statements, loops, or anywhere a condition is needed. It's important to remember that these operators are just as valid for characters as they are for numbers, thanks to ASCII encoding. And when using them, always be mindful of edge cases like x less than or equal to 3, which is true when x is exactly 3. Understanding these comparisons is key to building programs that make smart decisions. In many real-world programs, we don't just check for one specific value. We want to know if something falls within a certain range. That's where multi-branch if, else if, else structures come in. This slide walks through a soccer league example that classifies players based on their age. If the age is less than 6, it's Pee Wee soccer. If the age is between 6 and 17, it's the Junior Soccer League. Anything older falls into the professional category. The secret to getting this right is in how the conditions are ordered. Once a condition is true, all remaining branches are skipped. So in this example, we only need to check age less than 6, then age less than or equal to 17. The greater than 17 case is handled implicitly by the final else. This technique avoids overlapping conditions and makes the logic easy to follow. It's also a foundation for building robust input validation and data categorization. In this slide, we continue working with multi-branch if-else statements, but with a focus on detecting numeric ranges. This structure is useful for real-world decision-making, like mapping age ranges to ticket prices or classifying temperature zones. Each else if handles a range. For example, if a value is between 25 and 39, it might return a certain result, and so on. By clearly defining each range and checking in order, your program becomes more reliable and easier to maintain. When setting up your ranges, make sure there are no overlaps or gaps unless intentional. Each if or else if should be mutually exclusive to ensure only one block runs. This structure is ideal when your conditions involve not just single values, but ranges that must be handled differently. Next, we introduce the core logical operators in C: and, or, and not. These operators let you build more complex conditions by combining simple ones. The logical AND returns true only if both conditions are true. The logical OR returns true if at least one of the conditions is true. Finally, the logical NOT inverts the value. It turns true into false and vice versa. These operators are essential when writing decisions that depend on multiple conditions. For example, if a person must be both over 18 and have an ID to enter a club, that's a logical AND. If a person can enter with either a ticket or a pass, that's a logical OR. And if you want to exclude someone who's banned, that's where NOT comes in. These operators form the backbone of complex decision-making logic. Now let's look at how these logical operators are actually used in C. You'll most often see them inside if or else if statements. For instance, if you want to check that a user's age is between 18 and 65, and that they're not banned, you might use a compound condition with and not. This slide shows the syntax and expected behavior for each operator. It also includes truth tables and simple examples to clarify how they evaluate. Remember that these operators follow left-to-right evaluation and short-circuiting. For example, in an AND expression, if the first condition is false, C doesn't even check the second. It already knows the full expression is false. The same goes for OR. If the first is true, the second is skipped. Mastering these operators will help you write smarter, more efficient branching logic. A useful pattern uses logical OR to detect ranges with gaps. Imagine a policy where people 12 and under, or 65 and older, get special access. This isn't a continuous range, it's two distinct ranges with a gap in the middle. To handle this, you use the OR operator. For example, if age is less than or equal to 12, or age is greater than or equal to 65, checks both conditions, and if either is true, the person qualifies. This kind of logic is helpful in real-world applications like eligibility checks, user filtering, or exception handling. When using OR, make sure your conditions are truly independent or mutually exclusive. Otherwise, you might get unexpected results. Writing these compound conditions carefully helps your program model real-world rules clearly and effectively. Unlike multi-branch if-else chains, where only one block is executed, multiple distinct if statements are used when more than one condition might be true, and you want each of them to be checked. In this slide, we look at how to write several if statements that evaluate independently. For example, you might want to print a message if someone is at least 16 years old, and a separate message if they're 18 or older. In this case, both messages could be printed for someone who's 20. This approach is helpful when conditions are not mutually exclusive. Just be careful. Using multiple ifs where an if-else would be more appropriate can lead to logic bugs, especially if you assume only one block will run. Choose your structure based on whether the outcomes should be exclusive or cumulative. Next, we introduce nested if-else statements when you place one conditional block inside another. This pattern is useful when decisions depend on previous decisions. For example, first check if a user is logged in. If they are, then check their role. Maybe they're an admin or a regular user. The second condition is only relevant if the first one passes. Nesting lets you build this kind of layered logic. However, it's important to keep your nested code readable. Too many levels of indentation can quickly become hard to follow. One tip is to use curly braces consistently, even when each block has just one line. And if you find yourself deeply nesting logic, consider rewriting it with Boolean variables or breaking it into functions. Clear structure helps prevent logic errors and makes your code easier to maintain. Here, we look at one of the most common mistakes beginners make with if statements, forgetting to include braces. In C, if a branch only has one statement, the braces are technically optional, but relying on that can be risky. Without braces, it's easy to accidentally assume multiple lines are part of the branch when only the first line actually is. This often leads to logic errors that are hard to catch, because the program still compiles and runs. To avoid this, it's good practice to always use braces, even if you're only writing one line. This keeps your structure consistent and prevents accidental bugs when you come back later and add more code to the block. It also improves readability for anyone else looking at your program. Another very common mistake is using the wrong operator in a conditional expression. The most notorious example is using the assignment operator equals instead of the equality operator equals. This doesn't generate a compiler error, but it does change the logic. Instead of checking if x equals 5, you're assigning 5 to x and then evaluating the result, which is usually true. This can lead to completely unexpected behavior. Some compilers will give you a warning, but not all. Another common issue is using invalid combinations like equals, then greater than or less than greater than, which aren't valid in C. Make sure you're using only proper relational operators. Precision in your condition syntax is essential to avoid subtle and frustrating bugs. Understanding precedence rules is important when writing compound expressions. Operator precedence determines the order in which parts of an expression are evaluated, just like in math. For example, multiplication and division happen before addition and subtraction, and comparisons happen after those. Logical operators like and or have even lower precedence, which means if you're combining mathematical and logical operations, you need to use parentheses to make your intent clear. This slide provides a table showing how expressions are evaluated and emphasizes the importance of using parentheses not just for correctness, but also for readability. Even when you're sure you understand precedence, adding parentheses helps others and your future self understand what the code is supposed to do. Here are some common mistakes with logical expressions, specifically missing parentheses and writing math-style range checks. In C, if 16 less than age less than 25 does not check if age is between 16 and 25. Instead, it first evaluates 16 less than age, which returns either 0 or 1, and then compares that result to 25. That's clearly not what the programmer intended. The correct way is to use logical and. Age greater than 16 and age less than 25. This structure makes the condition both correct and readable. Similarly, if you're combining multiple logical operations, missing parentheses can make your expressions evaluate in the wrong order. Using parentheses is not just about correctness, it also makes your logic easier to follow and maintain. Be precise with your expressions, and you'll avoid these subtle but costly bugs. One easy-to-make but serious mistake in C programming is confusing bitwise and logical operators. The logical operators double ampersand and double vertical bars are used for combining Boolean conditions, like checking if a value is in a certain range. The bitwise versions, single ampersand and single vertical bar, are meant for low-level manipulation of bits and are not interchangeable. If you accidentally use single ampersand instead of double ampersand in an if statement, the condition still compiles, but the program may behave incorrectly. More importantly, logical operators use short-circuit evaluation. If the first condition is enough to determine the outcome, the second condition won't be checked. That's critical for writing efficient and safe code. Always use double ampersand and double vertical bars when evaluating conditions, and reserve single ampersand and single vertical bar for bitwise logic. The switch statement offers a clean way to handle multi-branch logic based on a single variable. Instead of repeating the variable over and over as you would with an if, else if, a switch lets you compare that variable to several constant values, each in its own case block. When the variable matches a case, the associated block runs. If no cases match, the default block provides a fallback. This structure is great for things like menu systems, command selection, or input validation based on single character or integer input. Just remember, each case usually ends with a break to prevent fall-through to the next block, unless you specifically want multiple cases to share the same outcome. When comparing switch statements to multi-branch if-else chains, the key difference is readability. Both approaches are functionally equivalent when comparing one variable to several constant values. But a switch avoids repeating the variable name in each condition and organizes your logic into clearly separated case blocks. For example, when determining a dog's age in human years, using a switch keeps the structure compact. An if-else chain works too, but it can quickly become harder to read if you have many conditions. However, keep in mind that switch only works with integer or character expressions. Anything involving ranges or more complex logic still requires if-else. Certain rules and best practices help make switch statements more reliable and easier to read. First, only use them with integer or character values. Strings and floating point numbers are not allowed. Each case label must be a constant, not a variable. Even though the order of cases doesn't affect execution, keeping them logically ordered improves clarity. It's also good practice to include a default case, even if you believe all possible values are covered. This provides a fallback and protects your program from unexpected inputs. And don't forget break. Unless you want a case to fall through into the next, a missing break can cause bugs that are tricky to spot. Leaving out the break statement causes fall-through, where control flows from one case into the next even if their values don't match. While this can be used intentionally to group multiple cases together, it's a common source of errors. For example, you might want dog ages of 0, 1, and 2 to all print the same message. That's a good use of fall-through. But if you forget to use break when you don't mean to, your program may run unintended blocks of code. To avoid confusion, always include break unless you're intentionally falling through, and even then, consider adding a comment to clarify your intent. Being deliberate with structure helps others understand your logic and helps you avoid subtle bugs. C includes a Boolean data type for representing true or false values, though it wasn't part of the earliest versions of the language. To use it in modern C programs, you include the standard bool library, which defines bool along with the constants true and false. Behind the scenes, bool is really just an int where 0 means false, and any non-zero value means true. For older C versions, like C89, programmers often define Boolean behavior manually by using typedefs and macros. A Boolean variable can be directly assigned true or false, or it can be set based on the result of an expression. For example, is hot equals temp greater than 90? Assigns the result of the condition to the variable. Boolean types make your code easier to read and understand, especially when naming conditions clearly, like is weekend or has access. Boolean variables become even more useful when they're used to simplify complex conditions. Instead of packing everything into one long if statement, you can assign the results of logical or relational expressions to individual Boolean variables. For example, a program might determine whether the weather is hot, really hot, or humid, then combine those conditions to decide what message to show the user. Assigning each test to a clearly named Boolean variable, like is hot or is humid, improves both readability and maintainability. It also allows for debugging by printing intermediate values or adjusting logic more easily. Using Booleans this way is especially powerful in longer programs where conditions are reused in multiple places. It helps make your logic modular and your code more expressive without adding unnecessary complexity. When comparing strings in C, a common error is trying to use the equals equals operator. This doesn't compare the contents of the strings, it compares their memory addresses. To actually check whether two strings contain the same characters, use the string compare function from the string.h library. This function returns if the strings are equal and a non-zero value otherwise. So a typical equality check would look like string compare of str1, str2 equals 0. One frequent mistake is forgetting to include the equals 0, which leads to always treating strings as unequal. Using string compare properly is essential whenever you're working with user input, checking commands, or validating string-based data. Just remember that string comparisons in C require a little more care than comparing integers or characters. Relational string comparisons are also handled with string compare, but instead of checking for equality, you're checking whether one string comes before or after another alphabetically. The function returns a negative value if the first string is less than the second, a positive value if it's greater, and 0 if they're equal. This is useful for sorting strings or checking order, like determining whether apple comes before banana. The comparison happens character by character using ASCII values. For example, capital A is 65 and lowercase a is 97, so capital letters are considered less than lowercase ones. To compare two strings relationally, use expressions like string compare of str1 minus str2, less than 0, or string compare of str1 minus str2, greater than 0. It's a powerful function for working with alphabetical data, but make sure you're interpreting the return value correctly. A string in C is really just an array of characters, and each character is accessed using an index. Indexing starts at 0, so the first character is at position 0, the second at 1, and so on. You can access a character using square brackets, like name open bracket, 2, closed bracket, and even assign a new value to a specific character in the array. But it's important to remember that all strings in C end with a special null character, written as \0, which marks the end of the string. This null character isn't counted by string len, so if a string contains hi, its length is 2, but its character array must be at least 3 bytes long to store h, I, and the null terminator. Working with character indices lets you inspect, modify, and validate strings at a low level. Just be sure not to go out of bounds or overwrite the null terminator unless you know what you're doing. C strings are mutable when stored in character arrays, which means you can change individual characters using their index. For example, if you have char user string equals ABCDA, you can change the fourth character by assigning user string of 3 equals x, turning the string into ABCXC. This is only possible if the string was declared as an array, not a string literal. String literals are stored in read-only memory, and trying to modify them can cause undefined behavior. Modifying strings this way can be useful for character substitution, simple encryption, or input sanitization. Just make sure you're not changing the null terminator at the end, since that would make the string appear to have no defined end. Modifying strings at the character level gives you full control, but requires care to avoid overwriting or misaligning memory. When working with strings in C, it's often necessary to access the final character. You can do this by first using string len to get the length of the string, then subtracting 1 to find the index of the last character. For example, if S1 is hey, string len of S1 returns 3, and S1 of 2 accesses the y. But keep in mind that the null character at the end is not included in the length returned by string len. Another common task is appending content to an existing string using string cat. This function joins the second string to the end of the first, assuming the first has enough space to hold the result. So string cat of S1, exclamation point, exclamation point, exclamation point would turn hey into hey exclamation point, exclamation point, exclamation point. Just be careful. If the destination array isn't large enough, you risk corrupting memory and causing unpredictable program behavior. Accessing characters in a string is powerful, but it can also lead to subtle and dangerous bugs if you're not careful with array bounds. In C, if you read or write beyond the end of a string, say, by using user text of 10 when the string only goes up to index 4, you could be reading garbage values or overwriting unrelated data. These errors often don't crash your program immediately, making them hard to trace. Even writing to user text of string len of user text is dangerous if it overwrites the null character, effectively removing the string's defined end. That's why off-by-one errors are so infamous in C programming. Always double-check your index calculations and make sure you leave space for the null character when copying or modifying strings. Using tools like string len and bounds checking logic helps you avoid these issues and write safer, more stable code. The ctype.h library provides a set of functions designed for checking and modifying character types. These functions help you determine whether a character is a digit, letter, whitespace, or another category. For example, isAlpha of C returns true if the character is alphabetic, while isDigit of C checks if it's a number. You also get isSpace of C, which detects spaces, tabs, or newlines. In addition to checks, the library provides case conversion functions like toUpper and toLower. These return the uppercase or lowercase version of a character, if applicable, and leave non-letter characters unchanged. For example, toUpper of A returns capital A, and toLower of Z returns lowercase c. Including ctype.h allows you to write cleaner, more readable code for parsing user input, validating characters, or building case-insensitive comparisons. These built-in tools save time and reduce the need for writing tedious manual checks. Conditional expressions in C let you simplify simple branching decisions into a single line of code. This is done using the ternary operator, written with the question mark and colon symbols. The general format is condition, question mark, value if true, colon, value if false. This example demonstrates that if x is 2, y is assigned 5. Otherwise, it's assigned 9 times x. This operator is called ternary because it involves 3 expressions. It's commonly used for short, inline decisions, like choosing between 2 values in a single assignment or return statement. While it can improve conciseness, it's best used sparingly. Avoid nesting ternary expressions or packing them with complex logic, as that can quickly hurt readability. In general, if the logic is simple, the ternary operator is great. If not, a full if-else block is the safer choice. When comparing floating-point numbers in C, it's important to avoid using the equality operator equals. Due to how floating-point values are stored, many decimal numbers cannot be represented exactly in binary. So even if 2 values look the same when printed, they might not be identical in memory. Instead of checking if x equals y, compare whether the difference between them is close enough. You do this using an epsilon value, a small threshold like 0.0001. The correct approach is f_abs of x minus y is less than 0.0001, which uses the absolute value function from the math library to ensure you're always comparing a positive difference. This method is especially important in programs that involve user input, calculations with decimals, or repeated rounding. Just remember to include math.h and choose an epsilon value that makes sense for your application's precision needs. Short-circuit evaluation is a feature in C that allows logical expressions to stop evaluating as soon as the result is known. For the logical AND operator, if the first condition is false, the second is never checked, because the whole expression is guaranteed to be false. For the logical OR operator, if the first condition is true, the second is skipped for the same reason. This behavior helps optimize performance and can prevent dangerous operations, like dividing by 0. For example, you might write if denominator not equal to 0 and numerator divided by denominator is greater than 1 to ensure the division only happens when safe. This strategy is especially useful when one condition guards the safety of another. Understanding short-circuiting not only helps you write more efficient code, but also protects your program from unintended runtime errors. In this lesson, we explored how branching allows programs to make decisions, enabling more dynamic and intelligent behavior. You learned how to use if-else, and multi-branch if-else structures to control which code runs based on certain conditions. We compared that to the switch statement and covered common pitfalls like missing braces, incorrect operators, and invalid comparisons. You also saw how to work with Boolean logic, character and string comparisons, and floating-point precision. We covered best practices for writing safe, readable code, and touched on advanced topics like short-circuit evaluation and the ternary operator. The ability to structure conditions and control flow is one of the most powerful tools in C programming. Mastering these fundamentals will help you write clearer, safer, and more efficient programs, and prepare you for more complex logic and algorithms down the road. Thanks for watching. Let me know in the comments if there are other topics you would like me to talk about. If you enjoyed this video, please like, share, and subscribe for more content on software engineering and technology. See you next time.